All right, cool. Welcome everyone. Thanks for coming. This week we're going to be doing more dynamic programming. So it's going to be a continuation of last week where we did an intro to dynamic programming. And so what we'll do is we'll do a couple of example problems. We'll do one called exploding batteries, and then after that we're going to look at something called longness increasing subsequences, and then we'll do one more example problem after that. And so yeah, we're going to start this week with just going over an example problem immediately, because we'll sort of just build off of the dynamic programming stuff that we covered last week. But before we do that, could you launch the poll on? Okay, cool. So we're just going to do a quick poll just to see how many of you came last week, and then in case enough of you didn't, we might have one breakout room that's we'll do like a recap of dynamic programming from last week. All right, cool. Yeah, I think we'll do one breakout room with a recap of dynamic programming, and then we'll have our other breakout rooms will sort of be going over the problem. But before we start on the problem, I wanted to quickly say a couple of tips to solve a DP problem. And so these are just some things that I just came up with, but this is sort of the steps that I take when I look at the DP problem. And I think, at least for the problems today, these are pretty helpful. So these are just things to keep in mind, I guess, while you look at these problems. So the first one is drawing out examples. And I think drawing out examples is probably applicable to most problems, but I think with DP especially, you can, if you draw out like a pretty large example, you can sort of sometimes look for patterns within it. And I think that sort of helps a lot with recurrences, is sort of figuring out how you get to a larger problem, like a larger example that you draw out from smaller things. And sort of similar to that, you want to look for patterns in subproblems. And the idea there is that when you draw out a large example, the ultimate goal of DP is sort of, you want to be able to figure out how you can break that down into subproblems. So essentially, assuming that you know something about a subproblem, how do you build, take that information and sort of combine it into getting information about a larger problem? So with that, I think both of these sort of go hand in hand with sort of drawing out examples and then looking for patterns. And hopefully this is something that we will be able to do with the example problems on this worksheet, and I think it'll also help with the contest. And then, yeah, another thing that I put on here is how would you solve it without a computer? And this, I think, is something that I sometimes think about. I don't know if it's as applicable to all problems, but sometimes I think when you see a competitive programming problem, especially a DP problem, sometimes it's obvious like how you could brute force it with different for loops and things like that. And sometimes it turns out that that might end up being too slow. So one thing that I think is helpful is when you have your large example that you draw out, if you think about like, how would you solve it without just like trying every single thing and sort of like trying to find the fastest solution that sort of you would do if you didn't have a computer. I think that's another good tip. And then one last tip for solving DP problems is looking for the base cases. So with this, sometimes this is even something you can do even before you've figured out what your occurrence is. And what you can do is sort of think about, for really small n, like maybe like a 1 element array or a 1 number sequence, and then maybe a 2 number sequence, you can sort of think about what the solution would be on those cases. And then from there, sort of see like, can you combine the n equals 1 case and the n equals 2 case to the n equals 3 case, maybe. And this is all kind of abstract, but these are just things that I think are useful to keep in mind while solving DP problems. And yeah, with that, I think we'll start our first example problem, and we'll just go straight into breakout rooms for this. And so I think what we'll do is you'll just make all the breakout rooms open to anyone. And so if you didn't come to last week's workshop, then maybe go to breakout room A. And if you did come to last week's workshop, then go to one of the other ones. And so in A, we'll sort of do a recap of last week and intro to dynamic programming. And yeah, otherwise, here's the link to the contest. And yeah, so I hope everyone got a chance to make some progress on the problem. So yeah, I think this, just to break down this problem a little bit, the idea is essentially that you're given a battery and it can only handle a certain level of current. And our goal is sort of to find out what the critical level of current is. So the idea is that we know that it'll explode at a certain current n, and it won't explode at current 0, and we're trying to figure out where in between will it also explode. And so we'll see how to do this with DP. But first, I wanted to sort of go back to the tips to solve a DP problem slide. And so I really wanted to emphasize that drawing out examples is, in my opinion at least, like the best place to start. And we'll sort of see how we can do this for this problem, and hopefully that'll help sort of visualize like how you can go about solving this. So I think I chose to sort of start by looking at the test case of n equals 6. And the reason I chose 6 is sort of, it's not too large that it's hard to compute, but it's also not too small that it's trivial. And so to sort of look at what the n equals 6 test case is, you have a battery here, and you know that it can sort of withstand a certain level of current. And so we're told that n equals 6. And so we can number these currents, I guess 1 milliamp, 2 milliamps, and so on up to 6 milliamps. And to break down the problem, what n equals 6 really means is that at 6 milliamps, the battery is going to blow up. And from here, we sort of want to know where exactly within these other choices is the battery going to blow up also, and where is it going to not blow up? And then we want to figure out like what's the place where it sort of transitions from blowing up to not blowing up. And the last part of the problem is that we're given 2 batteries to do this. So we have 2 batteries to test, and we're told that, so obviously like if a battery blows up, then you only have 1 battery left, and you're trying to figure out, in the worst case, what's the minimum number of tests that you're going to need to figure out the answer. And so yeah, I think that's just sort of how you can draw out the test case, maybe not with these sorts of pictures, but you could at least like, I think it's a good idea to sort of like, maybe like list out in tallies or something, and that's a good way to visualize this problem. And yeah, so the question is, how many tests are needed to determine the maximum safe current? And essentially we need to know like, we want to figure out how to optimally make these tests under the assumption that we don't actually know like where the maximum safe current actually is. So we need to sort of account for the worst case in that sense. And so what we're going to do is we're going to call this tests of 6. And this is just sort of a DP sort of thing where what you want to do is you want to sort of label questions sort of and problems with functions. And then that way, once you learn how to solve a certain function in terms of smaller functions or smaller problems, what you can do is you can create a recurrence relation of tests of 6 or tests of n using subproblems. And we'll see sort of how that works later. But for this, we can start by just thinking, what if we try 3 milliamps? And this is completely arbitrary to some extent, but the reason we choose 3, and we could have chosen anything else, is that, yeah, definitely don't hesitate to unmute. But yeah, the reason we chose 3 is, looking at this, we don't really know which one is the best. And ultimately, that's something that is kind of difficult to notice. And hopefully, while you were thinking about the problem, you realize that it's kind of it depends on what the number of test cases are. And so it can really depend. And because of that, we don't know what the right first choice of a test is. And so right now we're actually not picking the middle term. So this is just an example, but because we don't know which term to pick, we're actually going to pick every single term. And what we'll do is we'll pick every term and then we'll compare them. So that we'll get to that later, but essentially the idea behind DP is that, at least this problem, is that you want to sort of try everything and optimize it to a point where it's not too slow to try everything. And we'll sort of see how that works. So we'll start by trying 3 milliamps, but imagine that we're actually trying all 5 of these at some point and seeing which one is the best. But For 3 milliamps, the battery has sort of the test sort of has two cases. And the first is that the battery explodes, which is this. And then the second one is that the battery doesn't explode. And so if we look at this case, the battery explodes. And then what do we know from here? We know that, first of all, we lost these as cases because, well, we know that the battery explodes here. So there's no point in really testing 4 milliamps or 5 milliamps because we already know it explodes at 3. So it's going to explode for all the rest of them too. And so this is sort of interesting because now we've sort of cut down the problem a lot. And hopefully you guys see that this is kind of a much smaller problem and now it's a lot more approachable. And so yeah, along with this, we do lose a battery too. And so now we only have one battery, but we have these two currents that we want to test. And we want to know, like, does it explode at 1 milliamp? Does it explode at 2 milliamps? Or is it at 3? And so we have 3 cases here and we need to sort of figure out which one is correct. But we only have one battery to do so. So now what? We kind of have another choice now where we can either do 0, 1, or not 0. We could either test 1 or 2. And the idea is that, let's say we tested 2. And just for the sake of argument, let's just say that the actual amount that it could withstand was 1. And then we test 2 and the battery explodes. But now we're at a problem where we could have it being 1 or it could be 0. And we don't know, like, because we tested 2 first, we'll never know whether it would have exploded at 1. And because of that, now we're out of batteries and we have a problem. So essentially what this means is that we have to do 2 more tests. We have to start at 1 and then we have to go all the way up. Because when you only have one battery, and this is really key, is that you can't really make a guess without knowing for sure. So you have to sort of start with the first one and then work your way up. I see someone raised their hand. Yeah.
Yeah, I have a question. So I think I misunderstood the problem. So it's not about like you take one path and then figure out the worst case, but rather like assuming that you did take the best path, what's the worst amount of cases? Is that how that works? Why
Not
do you
quite.
like check every single battery in between? Because that's like, you need foresight for that, don't you? Like it's not a strategy if you.
Right. So you actually want to assume that you don't know what the correct answer is. So essentially what we're doing is test of 6 sort of determines the maximum number of tests required in the worst case. So what that means is that like obviously if you knew that let's say the answer was 4, right? Then you could theoretically just choose 4 the first time and then choose 3 the second time and you'd be done because you'd see that 4 blows up and 3 doesn't blow up. But and then the answer would be 2 always. But the idea is that you want to assume that you have no knowledge of what the actual thing is, and you want to sort of make guesses in a way such that you're guaranteed afterward to have, no matter what the initial thing was, you're guaranteed to have covered it as a case.
Oh, I see. That's why you check like everything in between the two, and then you take the minimum, right?
Exactly. Yeah.
Okay. Thank you.
Yeah, this problem is kind of confusing, but hopefully that helps. But yeah, that sort of hopefully also explains like when you have one battery left, you have to try every single thing and start at the beginning to make sure that you get to everything without the battery exploding. And yeah, cool. And so I think another thing that sort of helps is every time you get like a little bit of intuition about the problem, you can sort of start to write down an algorithm based on the part of intuition that you've got so far. And so what we've seen so far is that, let's say that the battery, so we tried K milliamps, in this case, K was 3, and we saw that the battery exploded on the first test. And in that case, we needed K minus 1 more tests. And where that K minus 1 thing came from is we had 3, and then all that's left is 2 and 1. So 3 minus 1 is 2 more tests are needed in the worst case. And then that plus your first test gives you K total tests required. And so this hopefully sort of shows we're sort of starting to build up an algorithm where in this case, we need K more tests. Cool. And of course, now we can sort of think about the other case where maybe the battery doesn't explode. And so yeah, maybe the battery doesn't explode. And now you know that this is okay, that the battery can withstand 3 milliamps. And then from there, you know now that it can withstand 2, it can withstand 1, it can withstand 0, and now you don't care about that anymore. So what you really have now is 3, 4, 5, 6, and you might be tempted now to think, well, it might be the same as last time now. You have to sort of try 4 and 5 and 6 and see what happens. But the difference between this one and the last case is that in this case, the battery didn't explode, so we still actually have 2 batteries left. And so this is actually kind of a different case, but hopefully it sort of looks familiar to something else. And what it looks familiar to, hopefully, is this. And the idea is that the numbers that I put at the bottom, they're just kind of like a way of labeling these lightning bolts, but they're not actually like part of the problem. Like I just did that to sort of make it clear like what each one represented, but you can sort of number these however you want. And the idea here is that this is very, very similar to the case where you started, where you had tests of 6 is equal to the green battery and then 5 of these bolts and then the red one. So this is basically a subproblem is what I'm getting at. And what we find from that is that this is test of 3, where you end at 3. Does anyone have any questions about this so far? Okay, cool. So yeah, let's just put this into the algorithm again. And so this was the second case where the battery doesn't explode on the first test. And then it becomes a subproblem, and that becomes tests of 6 minus k. And again, we got this because we shaved off 1 up to k. And so all that's left is whatever your ending was, which was 6 minus k. And so it becomes a subproblem of tests of 6 minus k. And so yeah, in total, 1 plus test of 6 minus k tests are required. And that's because you have the initial test where you tried k milliamps. And yeah, so from there, the problem actually does ask for the worst case. And so this is all great, but this only tells you, so you don't really know like which one between battery exploding versus not exploding. You don't know which one's actually going to happen. And because you want to sort of prepare for the worst case in some senses, you want to assume that the worst of the two actually ends up happening. And because of that, you take the maximum of these two results. And ultimately, when you try k milliamps, you sort of assume that the maximum of either k test or 1 plus test of 6 minus k is what actually happens. So you're sort of looking at, given a certain test, what's the worst case number of tests that will be required to do it? And this is sort of the recurrence relation. And so yeah, this is I think this is probably the trickiest part of the problem. And from here, we can sort of now go back to, well, we didn't actually know 3 milliamps was the correct start, but we want to try all possible k between 1 and 6. And so you try all possible k between 1 and 6. For each one, you take the maximum of k and 1 plus test of 6 minus k. But then from there, you wanted to actually start with the best possible starting test. And for that, you want to take the minimum of all of these cases. So this is sort of representing, this max part is representing the worst case number of tests that are required if you started at a certain k. But then we want to choose the best possible k to start at. So we take the minimum of the maximum of this. And yeah, hope that makes sense. If not, feel free to ask questions. But last part of the algorithm is generalizing from 6. And it turns out that's actually super easy. You just change the 6's everywhere to n's. And so now you have a formula for tests of n, where you try all the possible k between 1 and n, and then you calculate the minimum of the maximum of k and 1 plus test of n minus k. And I know this sounds kind of complicated, but I hope this sort of gives you an intuition of how you can sort of build a recurrence relation. And so yeah, this is what we end up with finally. And then the last thing is we want to do base cases. Oh yeah, sure, I can explain again. Right, so initially we wanted to choose a first k to test, and we want to choose k, and we want to choose the correct k in a way that we sort of minimize the number of cases, the number of tests required. So like, I guess as the problem says, we want to minimize the number of tests needed in the worst case. And that's the really key part of the problem, is we want to minimize worst case. And that ends up giving us both a min and a max, which is kind of confusing. But minimizing the number of tests means we want to minimize the, so I guess max of k and 1 plus tests of n minus k. This is the worst case given that you chose a specific k. And then from there, you want to minimizing means like you want to choose the k that would give you the best possible worst case. So you're sort of minimizing the worst case, which is why you end up with both a min and a max. Does that sort of help? It's a little confusing. Okay, hope that helped. Yeah, I'm gonna move on, I think. Okay, cool. And we can talk about this more in after if you want. But yeah, cool. Last thing is the base cases. And this is pretty simple. It's just if you already know that it blows up for even 1 milliamp, then you don't really need to do any tests because you already know the answer. So test of 1 is 0. And then from there, we can just go straight to the code. And I think one thing that's nice about DP is that even though the first part of it is really hard in finding the recurrence relation, writing the code itself is actually not too bad. And so the entire code is pretty much all in these 3 lines where we're told that n is between 2 and 4,711, right? So we start, I guess, by initializing our tabulation vector and doing our base case. And then from there, we know that n is between 2 and 4,711. So we just need to calculate these terms. And then this part is iterating from all k between 1 and n, and then just typing out our recurrence relation exactly. So the minimum of the maximum of k and 1 plus tests of n minus k. Then from there, this is just the input and output required to that the problem gives. So this is the number of test cases, or no, sorry, this is for a given n. If n is 0, then that means you're done with your test cases, so you end. Otherwise, you print out what you've tabulated for that answer. Yeah, does anyone have any questions about this problem? Okay, cool. Great, let's move on. So the next thing that we're going to talk about is longest increasing subsequences. So longest increasing subsequences is a problem that's basically given a sequence of integers, find the maximum length of an increasing subsequence. And so to sort of break this down a bit, let's look at this example. And this is a sequence of integers, 3, 5, 1, 2, 8, 4, 9, 7. And so an increasing subsequence is taking a collection of numbers within the sequence that are increasing. So every number is greater than numbers that came before it. And to give you an example of that, 3589 is an example of an increasing subsequence. So it's part of the sequence, but it doesn't have to be the whole thing. It doesn't have to be just one number. They don't have to be consecutive, but any set of numbers within the sequence. And it's such that every number is greater than numbers before. So it's like increasing from 3 to 5 to 8 to 9. And so the longest increasing subsequence problem is about finding the longest possible increasing subsequence. So in this case, it turns out that 3589 is the longest increasing subsequence. Just the sequence 1, 2 would also be increasing, but 3589 is length 4, so it has 4 numbers, and the goal is essentially to find the maximum length, so to find the longest possible subsequence. And to give you another example, this is the same sequence, but 1247 is also an increasing subsequence, and it turns out it also has length 4. And so both of these actually are examples of longest increasing subsequences, and it turns out that the longest increasing subsequence isn't unique necessarily, but yeah, the goal of the problem is really just to find the length of it. So either way, the answer is 4. And you can sort of think about this sequence and you'll see that there's no way really to get a longer sequence than this. Cool. Just to give a couple more examples, the number 7 itself is a sequence of length 1. And within that, the longest increasing subsequence is just choosing the number 7. And that's also a length 1 increasing subsequence. And then another example, let's say you had a sequence 5, 4, 3, 2, 1. All the numbers are sort of decreasing, so you can never really choose 2 numbers in a subsequence that will be increasing. So the longest increasing subsequence is length 1. It could be the number 5, it could be the number 3, it doesn't really matter, but you can just choose any number within, and you'll have a LAS of length 1. So yeah, I think what we'll do is I'll give you guys maybe like 5 minutes to sort of think about this problem. And yeah, I'd recommend like maybe drawing out an example and trying to see like you can see subproblems within it. And then in maybe like 5 minutes or so, we'll go through the idea for the solution. All right. Yeah, let's get started again. Does anyone have any ideas about the problem that they want to suggest, or otherwise I can just start? All right, that's fine. Okay, go ahead. Yeah, go ahead.
So basically, you can, I guess, have a function that takes in two inputs. One of them being the number of items that you want to consider from the list, and the other one being the maximum value of those items. And so, like, for instance, if we're taking the 5, 4, 3, 2, 1 example, you either choose 5 or you don't choose 5. So if you choose 5, then the length of the subsequence is 1 plus okay. It's going to be like 1 plus, and then the next case. Well, I guess. Okay, so five. The subsequence is 1, obviously, because I mean, if there's only one possible subsequence. So then you go on to 4, and you either choose 4 or you don't choose 4. And if you choose 4, then it's 1 plus the subsequence of the previous term, but with the maximum value of 4. So the max value of the max length subsequence, increasing subsequence of the first of like the one term where your maximum value is 4 is 0 because you can't pick anything. And then versus if you don't choose 4, then it's just the length of the subsequence with maximum value 0.
Okay. Yeah, great. I think that's pretty close to what it is. Yeah, I think that's pretty good. So yeah, I think that's great. So I think what we can do is we'll start by sort of drawing out examples similar to last problem. And so I think what we can do is let's just take this example, 3, 4, 1, 7, 8, 5, 10, 9, 2. And this example it's kind of a long sequence. The reason I chose this one is because it's not like one of those trivial sequences where you have like everything increasing or everything decreasing, but there's a lot of like increase and decrease and increase and increase, and it's kind of a lot of different increases and decreases. And so what we'll do is we'll do something that's actually really similar to that. And that is basically we want to sort of figure out what well, I guess to start, a longest increasing subsequence has to start somewhere and it has to end somewhere. And so based on that, we can sort of choose one of the two. And it doesn't really matter. I'm going to choose where it ends, but you could choose where it starts too if you want to. But let's just say we chose where it ends. And this is going to be pretty similar to the last problem where where you you sort of have to try every single number here as the last possible number in the longest increasing subsequence. But for example, we'll just try 9. But similar to the last one, we're sort of going to end up in the actual code iterating through all the numbers and then trying each of them as a possible last number. And so let's just consider the case of 9. And yeah, as Lap said, I think the idea from here is sort of we want to build an increasing subsequence that ends at the 9. So the challenge then is we want to figure out what numbers come before the 9 to create the longest possible sequence that ends in a 9. And well, we obviously can't put a 10 because 10 is greater than 9. But we could choose 5, we could choose 8, we could choose 7. Any of these could be the next number in the sequence that comes after or that comes right before the 9. And it turns out that this is the longest increasing subsequence, is if you have 3, 4, 7, 8. But ultimately, you do need to sort of test all of these. But yeah, so it turns out that there's a pattern with this, and that is that 3, 4, 7, 8 without the 9 is actually the longest increasing subsequence within itself. And what we notice is that if we focus directly in here, 3, 4, 7, 8 is the longest increasing subsequence among these first 5 numbers. So it's the longest increasing subsequence that ends in an 8. And that's kind of interesting because I think once we have the 9, we want to figure out, based on any of these possible other numbers as a choice for the previous number, we want to figure out which of them is going to contribute towards the longest possible increasing subsequence. So essentially, hopefully this gives you an idea of what's to come, but the idea is going to be sort of like you sort of keep track of the longest increasing subsequence that ends at a particular point, and then you sort of iterate through all of them. So yeah, that's just to give you an intuition. This is the LIS of the first 5 numbers, but to formalize this a little bit more, we'll look at a smaller sequence, and we'll also define LIS of n to be the LIS with the last number on the nth index. So this is sort of, for example, this would be LIS of 4 because it ends on the 4th index, but let's look at a slightly simpler example, which is 4, 3, 7, 5, 6, 8, 2. And just really quickly, the longest increasing subsequence here is 3, 5, 6, 8, so length 4. And so yeah, let's look at this and see how this would work. And for example, LIS of 2 is 2. This is, you could have 3 and 7 or 4 and 7, but LIS of 2 represents the longest increasing subsequence that ends on 2nd index, which is the 7, because we start at 0 and then 1 and 2. Yeah, so great. That's an example. And so now let's think about LIS of 4. And LIS of 4 is essentially the longest increasing subsequence that ends on the 6, right? So you want it to end on the 6 because 6 is at the 4th index. And the goal of DP is to sort of represent this in terms of previous numbers. And if you remember, we sort of saw intuition of how if you had a 9, you would want to sort of start from the previous ones. But similarly here, you want to sort of see how can you get to an LIS that ends in 6 from the previous one. So from the ones that ended in 4, 3, 7, and 5. And so what we'll see is first, we want to just figure out what these 4 are. And in DP, we'll kind of assume that we already know them and then sort of use that to make a recurrence. But in this case, we can just sort of calculate them pretty quickly. LIS of 0 is 1, which is just the number 4. LIS of 1 is 1, just the number 3. And notice here it's not 2 because 4 and then 3 doesn't work. But LIS of 2, the one that ends in 7, is 3 and then 7. And LIS of 3 is 2 also. It's 3 and then 5. It could also be 4 and then 5, but either way, the result is 2. So yeah, that gives you that gets you to this point where we've seen these 4 cases, and from here, we want to figure out, given that LIS of 0 is 1, it's just this 4. Given that LIS of 1 is 1 of just 3, we have the 3 and the 7 and the 3 and the 5. You want to figure out how do you get from there to LIS of 4. And well, so you sort of want, because you want LIS of 4, you want the LIS to end in the 6. So we can start there. We can consider the 6 and force that to be part of the sequence. And then from there, we know that we have these possible choices for increasing subsequences of the previous numbers. It could either, the previous number before the 6 could either be 5, it could be 7, it could be 3, or it could be 4. And so hopefully the first thing you guys notice is that 7 doesn't make sense because 7 is going to be larger than 6, so this isn't increasing. So you can cross this out. But all the other numbers turn out to be less than 6, which means that any increasing subsequence that ended in 5 can sort of be combined with the number 6 to create an increasing subsequence of length greater by 1. And so what we see here is that these 3 are all possible increasing subsequences. And more specifically, like if the number before the 6 was a 5, then this is the maximum way to create an increasing subsequence that ends in 5 and 6, because we already know that this is the maximum that ends in 5, and then just combining the 6 gives you the maximum that ends in 6 with the 5 before it. But for all we know, the maximum could have been achieved here, or it could have been achieved here. In this case, it turns out that the maximum is 3, and it's achieved by starting with the 5 before the 6, but it could have been here also. And that's sort of why in this case we sort of need to consider all of them. And so yeah, what we get from here is that LAS of 4 is equal to 3, because we see that there are 3 numbers circled here. And more formally, it means that LAS of 4 is 3 because you considered, you considered LAS of 0 as 1, LAS of 1 is 1, and LAS of 3 is 2. And then you took the maximum of those, which is the 2, because you want to take the maximum possible LAS below the 6, and then you add 1 to include the 6 as one of the numbers. So you get to 2 plus 1, which is 3. And so yeah, just to write this out in a little bit more math, to calculate LAS of n, you want to iterate through the numbers 0 through n minus 1. And that's iterating in this case from 0 to 3, which is 4 minus 1. And then if sequence of I is greater than or equal to sequence of n, and so that's saying, like, for example, if 7 is greater than 6, then you're going to end up with a sequence that's not actually increasing. So then you want to skip and ignore that case. Otherwise, out of all the other i's, I being from 0 to n minus 1, you want to consider the maximum of that LAS plus 1. Cool. So here's the code for that. It's almost identical to the math form. You'll see you create a sequence. This can be anything. Could be from standard input for a problem or anything like that. And then LAS is what we'll use as the vector that represents the LAS function, and it's sort of a tabulation vector. And so you start from 1, you go all the way to the end of the sequence to calculate each of the LASs. And for each one, you iterate from 0 to n, as the algorithm sort of said. And if the sequence at a certain point is greater than or equal to sequence of n, then you continue. Otherwise, you just plug in the recurrence relation essentially. And a couple of important things to note. One is that over here, we're initializing every value to be 1. Reason for that is because that's sort of a base case where for each number, the minimum possible LAS is 1, which is just the number itself. And then another thing is at the end, the answer isn't necessarily like, it's not going to be just LAS of n minus 1 or LAS of sequence.size minus 1. You actually want to consider the maximum number within this LAS vector, because for all we know, like in this case, LAS of 6, which would refer to the sequence that ended at 2, would only be 1, because there's no LAS that ends in 2. So you actually want to look at all of these numbers and see which one is the largest, and choose that to be the actual LAS. And that's what you would output. So yeah, anyone have any questions about this? Okay, cool. Sounds good. Great. So we're going to do one last thing before we move on to the second example problem. And this is that it turns out that there's an even faster way to do LAS. And this is something that's kind of a mix of DP and binary search, which is something that we covered last quarter. Don't worry about this method too much. The n-squared method, or this method that we showed here, the complexity of this, if you're interested in that, is n-squared, because there's 2 for loops, but it turns out that there's a way to do this that's faster, that is often helpful. So we'll go through that too. But yeah, the DP version, which is this one, is probably more important for this workshop. But yeah. So what I'm going to do to explain this algorithm is think about a stack of cards. So we're going to use the same sequence again, but think about the sequence as a stack of cards. So pretend that this is, we'll call this the deck. And then we're going to make a bunch of different piles over here. And the way it's going to work is that for each number at the top, the 4 is on top, and then it sort of goes down like that. But each number at the top, you take the top number, and you put it on a pile over here. Right now there's no piles, but the 4 will first become a pile and then you'll go from there. And for each number, if the number on a pile is larger than it, then you can put it on top of the pile. Otherwise, you have to move to the right and put it on the next pile. And this might seem like it's coming out of nowhere, but we'll sort of see how, we'll see how this helps with LAS. So we take the 4, we put it on the first pile, and then we take the 3, and the 3 is less than the 4, so we can actually put it on top of the 4. The 7 is larger than 3, so we create a new pile for the 7. 5 is larger than 3, so you move to the right. 5 is smaller than 7, so you put it on top of the 7's pile. And this is sort of like this is how we're creating our piles. I hope that sort of makes sense. And then with 6, it's larger than 3, it's larger than 5, so you create another pile here. Even though it's larger than 7, because the top of the pile is a 5, you move it to the pile on the right. And then 8 is larger than 3, it's larger than 5, it's larger than 6. So you put it at the end. And then finally 2 goes on the first pile, which is because it's smaller than 3. And so, yeah, so this is sort of the idea of this algorithm. And the interesting thing is that once you've made all these piles, it turns out that the 8 here is the last number in an LIS of length 4. And similarly, the 6 is the last number in an LIS of length 3. The 5 and the 7 are last numbers in LISs of length 2. And the 2, 3, and 4 are last numbers in LISs of length 1. And so now, keeping that in mind, we can sort of redo this whole process again, but sort of visualize it with the LIS construct at the same time. So obviously the 4 is an LIS of length 1. It's on the first pile, and any number can be thought of as an LIS of length 1, just the number itself. And now you add the 3 on top. And it goes on the same pile because it's not larger than the 4, which means that you can't create an LIS of greater length from the 3 and the 4, which is why we put it on the same pile. And for now, you can just see that the pattern still holds, that the 3 is still LIS of length 1, and it's not going on to the second thing because it's not an LIS of length 2. And now we get to the 7, and we see that we've already placed down a 3. And then if we place down the 7 next, we can take this 3 and then add the 7 to the back of the 3, and we'd get a subsequence that's increasing because 7 is greater than 3, which means that we can get a LIS of length 2 using the 3 and the 7, which means that now, by putting the 7 on the second pile, it symbolizes that we found an LIS of length 2 that's given by the 3 and the 7. And now we find the 5, and the 5 isn't larger than the 7, which means we can't create an LIS of length 3 because that would require the 3, the 7, and the 5. But what you can do is you can create an LIS of length 2, which with the 3 and the 5. And so sort of what these piles represent is the smallest number, or the smallest last number, in an LIS of length n. And now we can go to the 6. And the 6 is larger than 3, it's larger than 5, so we put it at the end. And what's important to note is that now you've come up with a LIS of length 3, which is the 3, the 5, and the 6. And this is interesting because now we have an LIS of length 3, so now you've created this third pile here with the 6. And then you go to the 8, it's greater than 3, it's greater than 5, it's greater than 6. And you can create an LIS of length 4 by doing 3, 5, 6, 8. And that's sort of why it ends up on the fourth pile. And finally, the 2 is smaller than the 3, so you can't really create an LIS with it. And so yeah, hopefully that sort of shows intuition as to why this works. It could be proved with induction, I guess, but we don't need to worry about that too much. But yeah, I guess the pattern just sort of ends up holding and working out, where each time you add to a new pile, it happens because you found a possible LIS of that length. And so yeah, just to summarize this really quickly, the idea is that for each element in the sequence, if an element is larger than all the piles, you create a new pile starting with that number. And otherwise, you update the first pile that's holding a larger number. So you put this on top of another pile. And then ultimately, what you want to return is the number of piles, because it turns out 8 being the largest, having 4 piles means that the largest LIS was length 4 and it ended in this 8. And yeah, it turns out, by the way, that you can't just read off these numbers as the actual LIS. You just sort of have to backtrack from the 8 and sort of think like, because the 2 ended up being added on top of the 3, even though it came after the 8. But if you sort of backtrack, 8 came after the 6, which came after 5, which came after 3. You can sort of reconstruct an LAS 3, 5, 6, 8, which you can get here. But that's not as important. But yeah, so that's sort of how this algorithm works. And returning the number of piles returns the length of the longest increasing subsequence. So yeah, here is some code that does this. It's a little bit more complicated than the last one, but the idea is now you're iterating from, well, I guess we can start with this. So you create a sequence 4, 3, 7, 5, 6, 8, 2. This is the same as in the previous example. And then you create your table. And this is the same sort of DP table. And the previous one was called LIS, and this we're just calling it table, but same idea. And the first part is creating your first pile. And your first pile starts with the first number in the sequence, which is sequence of 0. And then from there, you go through all the other numbers in the sequence that we call the deck, and you go through each number. Goal is going to be the name of that number. And you check, is it larger than my last pile? Last pile being what's currently in the table at the last element. And if it is larger, then you create a new pile for it. So this is what table.pushback essentially accomplishes. And then this is sort of the key part. We're using a function called lower bound, which I'm guessing a lot of you probably haven't seen before. But the way lower bound works is that it's a really efficient way of searching through numbers that are already in a vector and finding a specific goal. And specifically, it sort of finds a number that's the first index that's like less than or equal to the goal or greater than the goal. But yeah, essentially, the way it works is it uses binary search. And that's something that we covered last year or last quarter in Intro to CP. And so I've linked the slides here if you're interested in learning more about this stuff. And you can also look at the documentation for lower bound if you're interested. But yeah, essentially the idea is that lower bound is a really fast way of searching for a specific goal within a sorted array. So the key here is that if you look at these piles, because you always replace the minimum and each number is only placed to the right of smaller numbers, it's always going to be sorted, which means that you can do binary search to make this really efficient. And if you don't understand that, that's okay. These slides go through binary search pretty well, but the idea is that using this step, we go from an order of n squared approach, which was in the previous one, to order of n log n, which turns out to be a lot faster in a lot of cases. And yeah, ultimately table.size represents the number of piles total found. So you can just return table.size to return the length of the longest increasing subsequence at the end. So yeah, does anyone have any questions about this? Yeah. Rohit actually taught the binary search workshop last quarter, so he'll be great for answering those questions. And anyone else, of course, too. Yeah, great. If there's no other questions, we can move on to our last problem for today, which is called Prince and Princess. And just to give a little bit of context, this problem is going to be pretty related to this. And one of the reasons that I gave you guys this code is because this problem requires the nlogn version. But to some extent, I want you guys to sort of try to apply this. So feel free to just copy this part of the code if you want. But you're going to have to sort of make some modifications or figure out how to use this so that it'll work with this problem. Yeah, cool. We're going to do breakout rooms for this problem too. And yeah, Rohit will open them now, I think. All right. Yeah, hope everyone had a chance to look at the problem. And so what I'm going to do is, again, just sort of go through the sample test case. And yeah, I hope at this point, you guys are sort of starting to get a little bit of intuition in terms of how to sort of approach these sorts of DP problems where looking at examples is almost always the best first step. And so to sort of break this down, the problem is essentially asking us to find the length of the longest common subsequence, which is pretty similar to the longest increasing subsequence, except now you're given two sequences and you want to find within these two sequences, what's the length of the longest subsequence that appears in both sequences. So for example, here you have 1589 appearing in both, and because of that, your output is 4. And so yeah, let's think about how you could do this. And ultimately, you want to sort of boil this down to a longest increasing subsequence problem. And so what we can do is we can sort of focus on the second sequence, or we could focus on the first one, but just for the sake of example, we'll do the second one. And we want to ask ourselves, in this second sequence, how do we get, or what is the length of the longest subsequence that also appears in this first one? So sort of the second one is what we're checking, and then the first one is what we're checking against. And so the first thing that we can sort of observe is that the numbers 6 and 2, they don't appear in the first sequence, which means that when we're checking the sequence for common subsequences with the other one, we can just kind of ignore the 6 and the 2 because they don't really appear in the first one, so just they're not going to be part of a common subsequence. And then from there, you can, well, from there, it gets a little bit more tricky. So at this point, we've sort of simplified this second sequence a little bit, but now we want to sort of think about, well, so it turns out, I guess, in this case, that the longest common subsequence is 1589 in both of them. And in the sample test case, it turns out that that's also increasing, but that doesn't actually mean that we want to just take the longest increasing subsequence of the second sequence. Rather, we want to sort of think like, for example, 3 and 5 in this case is increasing in the normal way, but it's not really considered part of a common subsequence because 3 comes after 5 in the other one. And on the other hand, 4 is larger than 3, but 4 and 3 could be part of a common subsequence because 4 comes before 3 in the other sequence. So both of these are examples of how when you're looking at numbers and you're comparing them, you don't necessarily want to be comparing them based on like 3 is larger than 4 or 5 is larger than 3. You want to really think about it as 3 is larger than 4, even though it's actually smaller, because in this other sequence, it also comes after the 4. So the idea is that we're sort of looking at these numbers in the context of the other sequence, in the sense that 1 is considered to be smaller than 4, not because it's numerically smaller, but because in the other sequence, 4 comes after 1. Similarly, 3 is considered to be larger than 4 because 3 comes after 4. And to sort of boil this down to like what it actually means, we're looking at these numbers by context of their index in the other sequence. So we can sort of think about the indices 0, 1, up to 6, and we want to sort of think about these numbers in context of their indices. So we can sort of think of this as like a value of each of these numbers and then replace it. So rather than thinking of 1 as the number 1, think about it as the index 0. And similarly, think of 4 as the index 3, 3 as the index 5, and so on. And now what we'll notice is that even like in this case, we had the problem of 4 being smaller than 3, but actually being part of a common subsequence. But now we have that 3 is smaller than 5. So we've sort of turned the problem of common subsequence into the problem of increasing subsequence, where now these numbers in the second sequence are thought of in the context of the first one, which means that we can sort of look at an increasing subsequence within this, and that would be an increasing number of terms within the other sequence, and that can be used to choose a common subsequence. And so yeah, this comes from replacing these numbers with the indices from the other sequence, and you get 0, 3, 5, 2, 4, 6. And from here, you can just apply LIS to get 0, 2, 4, 6, which would output 4. And it turns out that that's pretty much it to the solution. And the idea of sort of replacing numbers with a different value is essentially the idea that LIS can sort of be generalized beyond just increasing subsequences to other things. So it can be used for decreasing subsequences. It can be used for common subsequences, non-decreasing subsequence, non-increasing subsequences. So there's a lot of different ways to sort of think about LIS, but the idea is you want to sort of come up with a value in a way of like, so we are looking for the longest subsequence of indices. Yeah, exactly. So we don't actually care about what the actual numbers are. We just care that their index in the other sequence is in increasing order, right? Because like, for example, 4 and 3, we don't care that 4 is larger than 3, but what we do care about is that 4 comes before 3 in the other sequence. So by considering their indices instead, by considering 3 and 5, we sort of turn this into a problem where now we actually care instead that the index of the 3 is larger than the index of the 4. And now we're considering an increasing subsequence where now we're considering 5 is greater than 3, which means that because 5 is greater than 3, even though 3 is not greater than 4, it'll be in increasing order in the other sequence. And this sort of boils down to like a subsequence is kind of defined as choosing terms in an increasing order, or like choosing indices in an increasing order. So like the subsequence could be defined as like, I don't know, the numbers 0, 2, 4, and then it would be subsequence would be 1, 5, 8. But that's sort of where the intuition for this comes from. And yeah, so we're just sort of trying to translate this into a problem where we can analyze the indices instead, and then them being increasing allows us to sort of apply LIS in a way that once we apply LIS to the indexes, you get 0, 2, 4, 6. And if you sort of refer back to this, 0, 2, 4, 6 represents 1, 5, 8, 9, which was the longest common subsequence that we had found initially. And so yeah, it turns out that that's pretty much it. How do we know the longest? Right, so I guess maybe if we go back to here, we have a subsequence 1, 4, 3, 5, 8, 9. And what we're trying to do is we're trying to find the longest subsequence within here that also appears within here. And what the longest increasing subsequence problem does is it finds the longest subsequence within here that's in an increasing order. And so what we're doing is instead of considering these numbers itself, by looking at the indices in relation to the other sequence, what we can do is we can sort of see like numbers increasing here means that they appear in the right order here. So by choosing the longest possible set of increasing indexes from here, so essentially we're choosing the longest possible subsequence of increasing indexes. And we can then look at those increasing indexes within the other sequence, right? So we can see we found 0, 2, 4, 6. We can look at that within the other sequence, and 0, 2, 4, 6 corresponds to 1, 5, 8, 9. And that ends up being the longest common subsequence where you have the same, because 1, 5, 8, 9, because it's increasing here, it means that it's a valid subsequence of the second one. And because the indexes are also increasing, it means that it's a valid subsequence of the first one as well. Does that sort of make sense? We can also maybe talk about this in the breakout rooms after, but since we're running a little low on time, I think, yeah, we can talk about this in the breakout rooms again, but since we're running low on time, I think let's just move on. We're pretty much done. The last thing is just wanted to give the code for this. I'm going to skip over this for now, but if you're interested, you can look at the slides later and see what the code was. It turns out to be a little bit longer, but ultimately it boils down to sort of translating to the indexes and then just using LIS. So yeah, with that, actually before we do the feedback form, one thing is that we're not going to have a workshop next week. We're going to take a break because of midterms. And so next week we won't have a workshop, and then we'll be starting again the week after, so week 6. Yeah, with that, please fill out the feedback form and give us feedback on this workshop. And yeah, after this, we'll move on to the contest. All right, hopefully everyone had a chance to fill out the feedback if you wanted to give us feedback. And yeah, with that, let's go to the contest. So let me put the link to the contest in the chat. And yeah, we'll do breakout rooms as usual. And yeah, the first problem on the contest isn't DP, it's more of a review of ad hoc. It's just a fun problem though. I think it's an interesting problem anyway. But yeah, the other four are all pretty related to this workshop. Cool.
All right, so I hope you guys stick around. I'm just going to make the breakout rooms where you can ask us questions about the workshop and also the contest problems. And you can just do it with us for maybe another 15 to 30 minutes. Normally, we do expect the workshop to run shorter, so you have more time to ask us questions, but we'll stick around a little longer today. Yeah.